Good morning, children. Welcome back to the lecture of chemistry. Today we are going to revise lesson number 10, that is halogen derivatives. What are halogens? In periodic table, there is a group 17, which is called as halogen, in which the halogens are placed like fluorine, chlorine, bromine, iodine and astatine. So fluorine, chlorine, bromine and iodine are important halogens. We can remember them by using the mnemonic fluorine, chlorine, break, iodine, atom. Now, what are derivatives? Derivatives are nothing but the derived form. When we attach halogen atom to organic compound such as alkane, which contains single bond, alkene which contain double bond, alkyne which contain triple bond, and aromatic or benzene ring, they are said to be halogen derivatives. Here you can see the example. Ethane, when treated with halogen, it becomes ethyl halide. Now, classification of haloalkenes. Depending on the number of halogen atoms, they are classified into monohalogen compound, which means 1, dihalogen compound, which means 2, trihalogen compounds, which means 3, and tetrahalogen compounds, which means 4. Depending on the nature of carbon halogen bond, they are classified into primary, secondary, and tertiary. Classification of halogen derivatives. Now, on the basis of hydrocarbon skeleton to which the halogen is attached, the halogen derivatives are classified as haloalkanes, haloalkenes, haloalkynes, and haloarenes. Now, let us see halogen exchange reaction. Now, in this example, you can see alkyl chloride when treated with sodium iodide in presence of acetone, it gives alkyl iodide and salt. So this reaction is called as Finkelstein reaction. So in Finkelstein reaction, we get alkyl iodide along with salt. Now let us study Sandmeyer's reaction. Aryl halides are most commonly prepared by replacement of nitrogen of diazonium salt. Now in this example, aniline is treated with hydrogen halide in presence of sodium nitrite. It gives diazonium salt, which on further reaction with copper halide gives haloarene. So in this way, Sandmeyer reaction takes place. Now let us study optical activity. The compounds which rotate the plane of polarized light are called optically active. A compound which rotates the plane of polarized light towards the right is called dextrorotatory. It is denoted by D or plus sign. A compound which rotates the plane of polarized light towards left is called as levorotatory. It is denoted by L or minus sign. Now here you can see that the light is rotating to the left side. So it is levorotatory, or it is also written in the form of L. Here the light is rotating to the right side. So it is called as dextrorotatory, or it is even written as D. Now let us study enantiomers. The optical isomers, which are non-superimposable mirror images of each other, are called as enantiomers. Equimolar mixture of enantiomer, that is dextrorotatory and levorotatory, is called as racemic mixture. It is denoted as TL or positive negative sign. Now let us study nucleophilic substitution reaction. When alkyl halide is treated with sodium hydroxide or potassium hydroxide, it forms alcohol. When alkyl halide is treated with sodium alkoxide, it forms ether. Ether is nothing but oxygen is present between two different alkyl groups. Now let us study nucleophilic substitution reaction. When alkyl halide reacts with NaOH or KOH, it gives alcohol. When alkyl halide is treated with sodium alkoxide, it forms ether. In ether, oxygen is present between two different alkyl groups. Alkyl halide, when it reacts with silver carboxylate, it forms ester. Alkyl halide, when treated with alcoholic ammonia in excess, it forms primary amine. Alkyl halide, when treated with potassium cyanide in alcohol, forms alkyl cyanide. Alkyl halide, when treated with silver cyanide in alcohol, it forms isocyanide. Alkyl halide, when treated with potassium nitrite, it forms alkyl nitrite. Alkyl halide, when treated with silver nitrite, it forms nitroalkene. Reaction of haloalkane with metals. Now there are two types of reaction, Grignard reaction and Wurtz reaction. Grignard reagent. Alkyl halide is treated with magnesium in presence of dry ether to give alkyl magnesium halide, and this is known as Grignard reagent. So alkyl magnesium halide is formed when alkyl halide is treated with magnesium. Wurtz reaction. In Wurtz reaction, alkyl halide reacts with sodium in presence of dry ether and it forms higher alkane containing double the number of carbon atoms than present in alkyl halide. So this is Wurtz reaction. It forms alkyl halide and salt. Wurtz fitting reaction. In this reaction, when aryl halide is treated with alkyl halide and sodium metal in presence of dry ether, it gives substituted aromatic compound. For example, bromobenzene when treated with methyl bromide and sodium in presence of dry ether, it forms toluene and salt. This reaction is an extension of Wurtz reaction, and as it was carried by fitting, this reaction is known as Wurtz fitting and it is used for alkylation of aryl halides. Nucleophilic substitution reaction. S stands for substitution, N stands for nucleophilic, and the order of the reaction, if it is 1, it is called as unimolecular, and if it is 2, it is called as bimolecular. Now this is SN2 mechanism. The nucleophile attacks the carbon undergoing substitution from the side opposite to that of the leaving group. This is to avoid steric repulsion and electrostatic repulsion between the incoming nucleophile and the leaving group. Now in transition state, you can see the nucleophile and the leaving group, both of them are bounded to the carbon with partial bond and carry partial negative charge. Thus, total negative charge is diffuse. The TS, that is the transition state, contain penta-coordinate carbon having 3 sigma bond in one plane and making bond angle of 120 with each other. And it has 2 partial covalent bonds along a line particular to this plane. So the product form is having opposite configuration compared to that of the substrate. In other words, we can say that SN2 reaction is found to proceed with inversion of configuration. So SN2 is bimolecular. It is one-step reaction. It attacks from the backside. It favors non-polar solvent and there is no intermediate form in this mechanism.
Conditions. Nucleophilic substitution reactions can be classified as SN1 or SN2 reactions. The S is for substitution and the N is for nucleophilic. Since these reactions are initiated by the nucleophile, the number gives information on the reaction kinetics, 2 for bimolecular and 1 for unimolecular. Let's start with the SN2 reaction. The reaction between 2-iodobutane and hydroxide ion to yield 2-butanol is an example of an SN2 reaction. This reaction follows second-order kinetics, meaning that the reaction rate depends on the concentration of both the nucleophile and the alkyl halide. As the slow step or rate-determining step involves 2 molecules, the mechanism is termed as bimolecular. This reaction occurs in a single step and does not involve any intermediate. Take note of the 3-dimensional arrangement of the atoms around the carbon in the alkyl halide. The solid wedge is used to show the bonds coming out of the plane of the screen. The dashed lines show bonds going down the plane of the screen, while the straight lines represent the bonds in the plane of the screen. In the SN2 mechanism, the nucleophile attacks from the back of the molecule on the opposite side from the halogen atom, the leaving group in this reaction. The leaving group leaves simultaneously. This is described as a concerted mechanism. That is a one-step mechanism because the new bond between the nucleophile and the carbon atom forms at the same time as that of the carbon-halogen bond breaks, as shown in the pentacoordinate transition state. Since the carbon atom is bonded to 5 atoms, the transition state is unstable and hence cannot be isolated. As the bond between the nucleophile and the carbon atom forms, the bond between the carbon and the leaving group weakens. The nucleophile essentially pushes the leaving group off the carbon atom. There is only one type of product in an SN2 reaction. If you compare the alkyl halide reactant and the substituted product, you can see that they have opposite stereochemistry. This switch is called an inversion of configuration. Can you imagine an umbrella being pushed inside out by a heavy wind? This is a useful analogy for understanding the SN2 mechanism. Let's apply our knowledge of
Now, SN1 reaction means substitution nucleophilic unimolecular reaction. In this, tertiary butyl bromide is treated with nucleophile. It can be seen in this reaction that concentration of only substrate appear in the rate equation. Concentration of the nucleophile does not influence the reaction rate. In other words, we can say that tertiary butyl bromide react with hydroxide in two-step mechanism. In the first step, which is a slow step, the bond between the carbon and halogen in the substrate undergo heterolysis, and in the subsequent fast step, the nucleophile uses its electron pair to form a new bond with the carbon undergoing change. So here you can see there are two steps in the reaction. In the first step, heterolysis of carbon and halogen bond, it is slow and reversible, and it forms a planar carbocation intermediate as it is shown in the figure. Then attack of nucleophile on the carbocation in the fast second step to form the
reaction between 3-bromo-3-methyl-hexane and hydroxide ion to yield 3-methyl-3-hexanol can be taken as an example of an SN1 reaction. The reaction shows first-order kinetics, as the reaction rate depends only on the concentration of the alkyl halide and not on the concentration of the hydroxide ion. The reaction occurs in two steps. In step 1, the leaving group departs, resulting in the formation of a carbocation. This step is slow and reversible. In step 2, the nucleophile attacks the carbocation, forming a covalent bond. The greater the possibility of the formation of a carbocation by an alkyl halide, the higher are the chances for the reaction to proceed via the SN1 mechanism. Further, the greater the stability of carbocation, the greater will be its ease of formation from alkyl halide, and the faster will be the rate of reaction. Thus, due to the greater stability of tertiary carbocations, tertiary alkyl halides readily undergo SN1 reactions. Allylic and benzylic halides also show high reactivity towards the SN1 reaction. This is because the allylic and benzylic carbocations formed get stabilized through resonance, as shown here. SN1 reactions are usually carried out in polar protic solvents such as water, alcohols, and acetic acid. The proton from the solvent molecules solvate the halide ion as it leaves in the first step of the mechanism. In the SN1 mechanism, there are two directions from which the nucleophile can attack the carbocation. Two different products can be formed from the SN1 mechanism. Compare the product that is formed when the nucleophile approaches from the left compared to when the nucleophile approaches from the right. They have the same formula, but different arrangements in space. These two products are mirror images of each other. They are not superimposable. Even if we rotate the right-hand molecule around the bond between the black and blue atoms, it still doesn't match the left-hand molecule. We call these as enantiomers. In the SN1 mechanism, both enantiomers are equally likely to form. This is called racemization. And such 50-50 mixtures are called racemic mixtures. You learn more about terms such as enantiomers and racemic mixtures, as well as about the stereochemical aspects of nucleophilic substitution reactions in the next module. You already know that an SN1 reaction proceeds with a complete racemization.
So SN1 is unimolecular, it is two steps, two transition state, backside attack and front side attack. It favors polar solvent. Intermediate is involved in the mechanism. Now halogenation reaction. Halogenation in haloarine is carried out in presence of ferric salt as Lewis acid catalyst. Here you can see chlorobenzene is treated with chlorine in presence of anhydrous FeCl3 to form two products. First is 1,4-dichlorobenzene and second is 1,2-dichlorobenzene. 1,4-dichlorobenzene is major product and 1,2-dichlorobenzene is minor product. So in this reaction, two products are formed. One is at 1,4 position, the other is at 1,2 position. Let's study nitration. Nitration is carried out by heating haloarine with concentrated nitric acid in presence of concentrated sulfuric acid. Now in this example, chlorobenzene is treated with concentrated nitric acid in presence of concentrated sulfuric acid. It gives two products. First is 1-chloro-4-nitrobenzene and second is 1-chloro-2-nitrobenzene. So nitrate group is obtained at fourth position and at second position along with chlorine. Sulfonation. Sulfonation reaction is carried out by heating haloarine with fuming sulfuric acid. Now in this example, chlorobenzene is treated with sulfuric acid. It gives two products, 1-chlorobenzene sulfonic acid and 4-chlorobenzene sulfonic acid. So sulfonic acid is obtained at one position as well as at fourth position. Friedel-Crafts reaction. Now it is carried out by treating haloarine with alkyl chloride or acyl chloride in presence of anhydrous AlCl3, that is aluminium chloride as a catalyst. A catalyst is a substance which increases or decreases the rate of reaction without itself undergoing any change. So here chlorobenzene is treated with methyl chloride in presence of anhydrous aluminium chloride. It gives 1-chlorotoluene and 4-chlorotoluene. So it is obtained at two different positions, that is first position and fourth position.